So when you talk about relative motion, yesterday we talked about derivative of a vector, right? Position vector. We looked at position vector and looked at the derivative of that position vector, right? So now think about okay. So what you're seeing here is, recall Newton's laws. So we talked about Newton's laws. Where are Newton's laws applicable? You guys remember? Anybody remembers? Yes?
As long as it's not in my speed of light.
No. Newton's laws, one of the assumptions of Newton's laws is Newton's laws are only applicable in an inertial reference frame. Okay? So you have inertial reference frame, and then you have a non-inertial reference. What is an inertial reference frame? You guys understand what is an inertial reference frame? So when you talk about inertial reference frame, a non-accelerating frame. Okay? And something which is non-inertial is accelerating. You have to get a little bit of context into what this non-accelerating frame is. What is non-accelerating in the universe? What body is not non-accelerating? What celestial body is non-accelerating? Earth is non-accelerating?
It's on the change direction.
Huh?
It changes.
Huh?
I don't think there is.
Also, it's already because it will be at tons of velocity.
So everything in the universe is actually accelerating. Acceleration means if it was not accelerating, what would have happened is it would have spiraled in. It wouldn't have. There are two components of velocity or acceleration. One acceleration is acceleration due to gravity. Okay. Yes.
What is the words of peace?
This is P. I'll come to that.
I think it's a positive fluid.
I'll come to that. So just think about this inertial reference frame or non-accelerating frame. A set of points moving with a constant velocity is an inertial reference frame, which that means a non-accelerating frame. Okay. Now Newton said his laws are applicable only in an inertial reference frame, which means if you apply Newton's laws in an aircraft, in a moving train, in a moving car, Newton's laws will not be applicable because unless those are moving at constant speed. So if something is accelerating, if you're moving in a car, unless you're absolutely moving at constant speed, if you're going fast or slowing down, Newton's laws won't be applicable. Newton's laws will not come true. Okay? So you have to think about an inertial reference frame. So inertial reference frame is something which is non-accelerating. So here what we're trying to understand is relative motion. Okay, this is important because everything in the universe is actually accelerating. Practically everything is accelerating. Earth is accelerating. If it does not accelerate, it will spiral in. There's this component acceleration due to gravity. If Earth does not accelerate, it will be pulled in. Okay. So here what you're seeing is, so think about this point. This is a point P of interest. Okay. Now let's say this is the orbiting body. This is the reference frame, small ijk is the reference frame of Earth. Okay, this is rotating with respect to Earth. This is the R relative, is the relative position of this P with respect to Earth's center. Okay. This R0, so assume this capital Ijk is one inertial reference frame. It's somewhere. Okay. This R0 is the absolute position of Earth's center. And this R is the absolute position of this point P. Right? Now what is this R?
You say R not is the point, the absolute, wait, say it again?
R0 is the absolute position of this point O.
Okay,
This is point O.
okay.
Okay? So this R0 is the absolute position of point O. R is the absolute position of point P.
Okay.
And R relative is the relative position of
O to
point P with respect to O.
Okay.
Now if you look at R is simply R0 plus R relative. Everybody agrees with this? This is the law of parallelogram, right? So it's just a vector. Now, R relative, here think about how do you express R relative. R relative is, you can say this is small x I plus y j plus z k. Okay. This is the x component of R relative, y component, z component, and it is the I, j, k. Okay. You can also just write this as, this would also have this is also okay. Now if I take the derivative, let's take the derivative of this. d over dt of R is equal to what?
R dot X I.
d over dt of, so here is what you are going to get, R0 plus R relative, right? So here, you look at R0, What is R naught? How would you express R naught? R naught would be capital X, okay? I,
Yeah, and then capital Y,
capital Y,
J,
J,
and then capital T.
capital Z, right?
So this because we're using the first point, like the Earth's relative point, right?
Right.
Okay.
So here, this is how you would express R naught. Now, you tell me what is the difference between this ijk and this ijk?
Two different.
With respect to? Are these ijk changing?
Yeah.
They're changing because this is rotating. This is a non-inertial reference frame. Okay, this, let's call this, when I put this hash mark, this means this reference frame is inertial or it's fixed. And this is the non-inertial reference frame, which is, it is moving. So this ijk, small ijk are changing. Okay.
This is like local and global coordinates.
Yes,
Which
yes,
one
something.
is the global coordinate?
So this is like, this is the global, and this is something like global. So here, yes, you're right. So it's in that context. Okay. So now this is, now you understand if I take the derivative of this, what would it be? X dot, Y dot. Sorry, this won't be necessary, right? So the components don't have a direction. Components these are just magnitudes, right? X, Y, Z. So it would be X dot, Y dot, Z dot. But what would this be? The derivative of this. So here if I take this, it will be
Will change.
X dot I plus Y dot J plus Z dot K plus X I dot plus Y J dot plus Z K dot.
We saying dot for I, J, and K for the relative because that's the one that's changing, right?
Right, just be with me here. Plus, so this is the derivative of this.
Right, and that's the okay.
Okay? So hang on. Let me just put this. So here is plus X dot I plus Y dot J plus Z dot K plus X I dot plus Y J dot plus Z K. Okay, this term is d over dt of r dot, which is equal to, let's say, v dot or v naught, and this term is d over dt of r relative, which is equal to, which we represent using v relative. Okay. Now, what you should realize is these terms go to 0. Why do these terms go to 0?
This is for
Because this one is constant.
Because these ijk
aren't changing.
aren't changing. When I say that hash mark, it is fixed.
Okay.
It's not changing. It's with respect to time, ijk are not changing. Okay, this point is moving around. This is also moving around. This earth is moving around, right? So this means this r naught is changing. If I express r naught like this, if I take the derivative of this, it's going to be like, you are going to use a product rule on this one, right? So I've used the product rule and put But here it so happens that I dot, j dot and this capital Ijk dot will go to 0. But that is not the case here
Look at the change.
because this is continuously changing. Okay, so the way we write this is V naught plus d over dt of r relative, which is V naught plus V relative plus V
Is that a set equation?
Huh?
Is that just like a set equation?
So yes. So this. Do you understand what this V naught is?
Yeah, I'm talking about the next one down. Where you got
Right. Let me come to that. So this is. You understand this V naught?
Yeah.
That's the R not.
So this is something. This is this V naught. Okay. This is this.
Yeah.
Got it? I've just put this here. Now this one, this V relative is this component. Got it? This is expressed, this can be expressed as cap omega cross with
R.
R relative.
What does that mean?
It means this is angular velocity of this. Angular velocity crossed with R relative. This is that term. Okay? That's what you have to keep in mind. You'll understand it when you do this a number of times. If you repeatedly do this, you'll understand it. Get it? So this you understand what term this is? This omega will come into picture only for a moving frame. If both of these were
Station.
stationary, this would just be
0.
0. This part would be 0.
But
You
that
have
won't
only
be
these two.
same.
Yes.
So basically because that body itself is moving.
Yes,
it's all
yes.
angular rotation.
Right. So if think about you're going in a plane, okay, and there is a you're moving in the plane as well, and there is a air traffic control. Air traffic control itself is not moving, right? So your position, we are trying to figure out your velocity. This is your velocity in the plane as you are moving. Okay. Now this is the velocity of the plane itself. This is your velocity inside the plane with respect to the plane. Got it? Now we have to take into consideration the origin of the plane is this. You think about one point in the plane, but the plane is also doing this. Right? So this captures that aspect. So this is the total velocity, the absolute velocity, your absolute velocity with respect to the air traffic control. Got it? So this is how you express it. If now this does not have anything. This air traffic control itself is not stationary. It's not doing anything. So this becomes okay. So this is relative motion. All right. Now acceleration. What do you do with acceleration? So if you want acceleration, you have A is d over dt of V, which is equal to d over dt of V naught plus
0.
V relative plus omega cross with
R.
R relative. Okay, so this would be this d over dt of V naught is what?
Is this A?
You have to now there's a general rule. You have to apply this general rule, and that general rule is here. Okay, the derivative of any vector, if you have a vector, I'll write it here, for any vector A, d over dt of A we will always use this notation. This is A circle dot plus omega or cap omega crossed with A. Now keep this in mind, and we have actually applied this here. We have applied this here, right? If you look at this is vector A, right? We applied it here. So this would have been R naught circle dot, which is this V naught, plus omega crossed into R naught. But what happens is this omega is 0 for this R naught, right? Because this is not moving. And then if we apply this again for this vector, it will be R relative circle dot, which is V relative, plus omega crossed with R relative, and that's what you see. There are two vectors, we have applied both of these, this law to both of these vectors.
What is the A circle dot?
A circle dot is the local derivative here. Got it? So this A circle dot would be this one, the local circle. Okay. So here again, what we need to do is, if we just stick by this rule, you're going to get V naught circle dot plus omega cross with V naught. So this would be 0. Right? This whole thing would be 0 because this V naught is coordinatized in a reference frame which does not have any angular velocity. Plus V relative circle dot plus omega cross with V relative plus omega cross with R relative, this whole circle dot plus omega cross with R relative. It will be that way. So you have to just do it. See, this is math. Math is very methodical. If you do it, if you stick to your this thing, if you are disciplined, you'll not go wrong in math. I have not done anything. Everything is disciplined here. I just use this one to each of those vectors. This is one vector. You understand? This is just another vector, right? So this is V naught. This goes to 0. This V relative cross with. This is just a derivative, local derivative. Okay. Plus omega cross with V relative, and I have taken this plus this. Got it? So you should
The dot you got there on the last part is over omega.
So this is equivalent to writing. So here this term, right? We're talking about. This is equivalent to writing d over dt of omega cross with R relative. Got it? And this expands to okay. So this is your complete acceleration. Now I can write A is equal to
Did you just rewrite it?
V naught plus V relative plus
Why is the dot only over the omega, not the omega times the relative? On the
This
second
one?
row, yeah.
So this is the entire thing. This is equivalent to saying this. You mean this, right?
Yeah, because when you rewrote it, you only have it over the omega, right? Underneath.
No. So what I did was this I brought it here. This I brought it here.
Mm-hmm.
This I brought it here. When I do this, when I do this.
Oh, you expanded the.
Yes. So
Okay.
this is the rule for. So
Okay.
it is very similar to the product rule, except there's a negative sign when it comes to cross product. I've used the derivative of this cross product is this times this minus this derivative times r.
Okay.
So that is how it expands.
Okay.
And what I do is I just bring this whole thing here.
Okay. Yeah, I see.
Okay. So what you're going to see here is okay, this alpha, so here these two, what is this? This is simply omega crossed with V relative.
No, it's the. Wait, huh?
R dot, R circle dot is
The derivative, right?
derivative of R relative, right? So that is V relative. Okay, so this two have combined to omega crossed with V relative minus this omega derivative of omega. Omega itself is angular velocity. This becomes angular acceleration.
Wait,
Alpha
say that
is
again.
angular acceleration. Huh?
Say that again.
This omega, cap omega, everybody understands that cap omega? That is angular velocity. When you take the derivative of angular velocity,
okay.
it becomes
Okay.
angular acceleration,
Okay.
which is denoted by alpha, crossed with r relative, and this term remains as it is. Yes.
In the book, they had some lowercase and then different capital, like up, like how you have on the board. Is there a difference, like one we should use which symbol?
It doesn't matter actually. See, if you want to distinguish between the angular velocities of two reference frames, here, let's say there are three reference frames, okay? Then you may want to, and only one of the two reference frames are having angular velocity. So one you can use just like this. This is cap omega, and that w, small w is the small omega, right? If you have three reference frames and two of them have angular velocities, one you can use cap omega and the other you can use.
Because you wouldn't be able to add those two
You
angular
cannot.
thing. You would.
You cannot, right? You
Yeah,
cannot
okay.
add them if you get them. So you have
Right.
to distinguish between those.
Okay.
That's the only thing.
Yeah, yeah.
So I think this is plus. Um, yeah, this is plus. So this, take this down as well. This is one more note. Let me write it here. d over dt of A cross B is equal to A cross B dot, okay, plus or minus B cross
A dot.
A dot. Okay. Now this would also be equal to, if I shift this, A cross B plus
A.
A dot cross
Wait, that B should have a dot though, right? Are you doing addition? Okay.
So this is what I have done. What has happened here. It was the other way around. So this is, you have to follow this rule. A derivative of A cross B. You remember product rule? Derivative of A into B is what? A derivative of B plus B derivative of A. That's what you do, right? For product rule. So here it is opposite.
So it's negative.
It's negative.
Switching, and it's positive.
Yeah.
So if you A cross B is negative B cross A. That should also be, you should be aware of that as well. A cross B is equal to minus B cross A. And that's where this comes into. Okay. Now here is what your absolute acceleration is. And here, if you look at this, you've heard about this Coriolis term. When you have acceleration, you have linear acceleration, you have Coriolis term, you have centripetal term, you have centrifugal term, right? Where do those come from? If you analyze this equation, all those terms are in there. Got it? So you should be able to apply, this law is very, very important. This general derivative law is very important. Now you understand relative motion. Do you get an understanding of relative motion and why relative motion is important for space mechanics?
I don't know why it's important for space mechanics.
Because when you launch, I'll just take 2 more minutes. When you launch something in space, you want to know where it is, right? You want to know where it is with respect to
The Earth.
Earth, relative to Earth. You want to know relative to Earth. Can you know absolute?
You should know.
There is nothing like absolute. You'll always want to know relative to something. Relative to Earth, relative to Moon, relative to Mars. When you talk about other planets, you say relative to Sun. Sometimes you want to know relative to Earth. So it's always relative motion. It's always relative position. So this is that relative position. Got it? So what we are interested in is, we can always, if we know relative motion, we'll know, we cannot apply Newton's laws to relative motion, but this is how we can apply it. So if you assume this inertial reference frame exists somewhere, you figure that out and you can extract whatever information you have. Got it? So this relative motion is very important because everything in space is relative. Next class, we are going to start with the actual orbital mechanics. Please pass me your attendance if possible. Did you have attendance?
No.
Can you quickly